You can get oscillations near local maxima and minima. Here is an equation of x squared plus 2 which does not have any real roots. X squared plus 2 equals 0 does not have real roots, which you can see that if you look at the graph of x squared plus 2, it doesn't cross the x-axis anywhere. But you could start with some initial guess trying to find out the roots of this equation, because you can surely set it up in Newton-Raphson method formula, this particular equation. And so this is what happens. Let's suppose you start with -1, which seems to be a good place to start, where you take the tangent, you end up right here. Then you go up here, you draw the tangent again there and see where it crosses the x-axis. It's crossing right here. You go all the way up to right here, and it crosses the x-axis. The tangent crosses the x-axis right here, and then you go all the way up to there. Tangent crosses the x-axis all the way there. Now you might think that it's diverging. No, actually it's not diverging. It's going to come back and start oscillating again back around the local minima here, which is at x equal to 0. So that can happen when you are using Newton-Raphson method. Again, you have to understand that this equation does not have any roots between x equal to, does not have any real roots. So, but still, if you want to use Newton-Raphson method algorithm, you find out that it starts oscillating between one point and another and starts getting closer and closer to x equal to 0. Not closer and closer, but it will start oscillating around x equal to 0 as you conduct more and more iterations. This is another issue which you can have when using Newton-Raphson method on equations. So if you have equations such as this, x minus 1 whole cube plus 0.512 equal to 0. Now what is different about this particular equation is that it has an inflection point at x equal to 1. So at x equal to 1, there's an inflection point. What do we mean by inflection point? Is that you have concavity changing to the left of it and to the right of it. So here it's concave up, here it's concave down. So that particular point is called an inflection point. And one of the ways to find an inflection point in a function is to see that if the second derivative of the function at that particular point is becoming 0 or does not exist. That does not make it to be an inflection point. Just because the second derivative is 0 at a particular point does not make it an inflection point. It makes it a candidate for inflection point. Now, since in this case the second derivative is going to be changing sign to the left of it and the right of it, because if you look at the second derivative of the function will be 6x minus 1, and you can see that at x equal to just before minus 1 it's negative, just after plus 1 it's positive. So since the second derivative is changing sign across the inflection point, we know that this is an inflection point. And now what happens in Newton-Raphson method formula is that you may start with a good guess of 5, which does not seem to be a bad guess to be finding out the exact root of 0.2. 0.2 is the exact root of this particular equation. And you find out that you start with the initial guess of 5 right here, and when you apply the Newton-Raphson method formula, it starts getting closer and closer to 0.2, which is the exact value. But now what you're finding out is that at this particular point at 0.9259, it is getting closer to the inflection point of x equal to 1, and it starts diverging. It goes to minus 30 as the next iterated value. But again, what happens is that in this case it starts again to converge, and after 12 more iterations it converges on the exact root of 0.2. So you are going to have issues with equations which have inflection points which are close to the root. And that's the case here. So here we have an inflection point x equal to 1. The root is at 0.2. This is what the root is. And if you find out that any of the initial guesses or the iterated values turn out to be close to the actual root, you are going to have some divergence problems in the Newton-Raphson method. And that's the end of this segment.